This video explores programming methodology, the art of human-machine communication. We will bridge the gap between human abstract logic and binary execution through the C language. We will cover defining logic, learning the C environment, mastering the grammar, and starting the conversation with input and output. The core challenge lies in the communication gap. Humans think in natural language, while machines only understand binary digits, zeros and ones. Using machine code directly is fast but error-prone and requires memorizing thousands of opcodes. This gap led to the evolution of language. First-generation machine language is fast but machine-dependent. Second-generation assembly language uses mnemonics, but still requires translation. Third-generation high-level languages like C use English-like instructions, offering portability and easier debugging. Programming languages rely on translators. An assembler converts symbolic assembly into machine code. A compiler translates the entire high-level program into machine language at once. An interpreter translates and executes the program line by line. C uses a compiler, separating the code writing from execution for better optimization. Before writing code, we need a blueprint, the algorithm. An algorithm is a step-by-step, finite set of instructions to solve a problem. Core characteristics include being unambiguous, finite, feasible, and having defined input and output. Flowcharts are used to visualize logic. Standard symbols include the terminator for start/stop, the parallelogram for input/output, the rectangle for process or calculation, and the diamond for decisions or branching. C language was developed by Dennis Ritchie at AT&T Bell Laboratories in 1972. It is structured, portable across different systems, and middle-level, offering high-level readability with low-level hardware access. It is standardized by ANSI to ensure consistency. The program development cycle, or the workshop, involves 5 steps. The editor writes the source code. The preprocessor handles directives. The compiler translates the code to object code. The linker combines object code with libraries. Finally, the loader loads the executable into RAM for execution. The anatomy of a C program includes the preprocessor directive, such as including the standard input/output library. The entry point, ;void main, is where execution begins. Braces define the scope of a function, and statements like ;printf, ;execute instructions, ending with a semicolon. The C character set includes letters, digits, white space, and special symbols. Tokens are the smallest units of a program. Keywords are reserved words with fixed meanings. Identifiers are user-defined names, which must start with a letter or underscore and are case-sensitive. Data containers come in 2 forms: constants and variables. Constants are fixed values that do not change. Variables are named memory locations, whose values can be updated. C is strongly typed, meaning all variables must be declared with a data type. Primary data types include int for integers, float and double for real numbers, and char for single characters. Qualifiers like short long signed and unsigned can alter the size and range of these types. To start the conversation, we use printf, for formatted output. This function includes literal text, conversion specifiers acting as placeholders, and arguments, which are the variables to be printed. Escape sequences like and control formatting. For formatted input, we use scanf. Like printf, it uses a format specifier, but crucially, it requires the address operator, and to deposit data into the variable's memory location. For unformatted I/O, getchar, reads a single character, and putchar, displays it. For strings, gets, reads an entire line, including spaces, and puts, prints a string followed by a new line. This contrasts with scanf, which stops input at the first space. This cheat sheet summarizes the essential C language syntax, including data types, format specifiers, escape sequences, and core I/O functions. Mastery of these building blocks is key to translating algorithms into executable reality.